Hello and welcome to Lecture 17 of Foundations of Artificial Intelligence. Today we're first going to learn a little bit about agents, and then we're going to dive into an introduction to search. In our last lecture, we talked about different biomedical expert systems, including clinical decision support systems, Dendral, Mycin, and some other various biomedical expert systems as examples. We'll begin today's lecture by looking at intelligent agents as its own separate topic, and then we'll go into an introduction to search. We'll talk a little bit about visualizing search and some of the basics of search algorithms. So first off, let's talk about intelligent agents. First off, what's an agent? Here's a definition from Russell and Norvig. An agent is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through effectors. Here's a simple schematic illustrating the basic idea of what an agent is. Here we have the agent itself, which can be seen as an autonomous entity, which can sense things from its environment using perceptors. This serves as the input to the agent. Using this input, the agent can make decisions and decide on some action or output, and this is usually returned to the environment or some action occurs in the environment. If there's an interaction with the environment, the agent will use its actuators to do its chosen action. If we define the environment as whatever provides input and receives output, then effectively any program can be viewed as an agent. However, more commonly, agents refer to some autonomous entity, perhaps a robot, or some other kind of autonomous decision maker tasked with a specific goal. Let's cover some other terminology regarding agents. First off, we have the sensor. This monitors percepts, and an example of a sensor could be a camera, a keyboard, or anything like that. An actuator allows an agent to act upon or within the environment. The percept mentioned above is the agent's perceptual inputs at any given instant. A percept sequence is the complete history of everything the agent has perceived. An agent function maps any given percept sequence to an action. This can be based on some mathematical concept or decision-making model. Then we have an agent program. An agent program implements the agent function within the context of a specific agent. Towards understanding agents, let's now talk a little bit about rationality. We learned a little bit about rationality in our introductory lecture to AI. Recall that research in AI can be about making systems that act or think either rationally or humanly. When an agent is being developed, there's usually a fixed performance measure that evaluates the environment sequence. A rational agent chooses whichever action maximizes the expected value of that performance measure given the percept sequence to date. Here we're diving into agents as if we're dealing with multi-step problems, which might be the purview of something like reinforcement learning. However, we can also think of agents as dealing with supervised learning situations where we have a single input from the environment and we want to make a single decision. One thing to note about rationality is that a rational agent isn't necessarily omniscient or clairvoyant or even necessarily successful. Having a rational agent is all about having an agent that can explore, learn, and act autonomously. Let's take a look at a really simple example of an agent. We'll use this toy problem of a vacuum cleaner world. Here we have only two positions in the world, A and B. We have a vacuum cleaner, and in this case we have dirt in both A and B to start. So our percepts of our, let's say that our vacuum cleaner is an autonomous agent, such as a Roomba. This agent can percept its location, in other words, is it in A or B, and the contents of that location. In other words, am I currently in A or B, and is there dirt in my location? So in this first example, our agent is at location A, and that location is currently dirty. The actions that are available to this agent include moving left, right, sucking up the dirt, or doing nothing. Here we have the percept sequence and the action taken at each step. If A was clean, we'd want to move to the right to cell B and see if it was clean. If A was dirty, which it is in this case, we'd want to suck up the dirt. And we can imagine a number of other scenarios playing out afterwards. Now we'll step through and look at some increasingly complex variations of agents. We'll start with a simple reflex agent. Here we have our agent encapsulated by this box, and here's our environment over here on the right. A reflex agent would sense something from the environment, such as the state of the environment at this current point, and then based on that current state, we'd have pre-programmed condition action rules that might trigger or not trigger to determine the next action to take. This chosen action would then be affected in the environment, using, for example, an actuator. So the purpose of a simple reflex agent is simply to respond to the conditions in the environment and use a set of pre-programmed rules to make decisions and determine the behavior of that agent. Further, in this simple agent example, the agent has no memory of the decisions it's made in previous steps, or a memory of the state of the environment that came before it. So let's go back to our vacuum cleaner world example, where we start in the same states we saw before. We can see a series of if-then rules underlie the behavior of this reflex agent. The input includes the current location and status, dirty or clean. And in this case, if the status is dirty, then the chosen behavior is suck. Otherwise, assuming that the state is clean, if the robot's in location A, then move to the right. Otherwise, if it's in location B, and again, we have a clean state, then we go to the left. In this case, the decisions right or left might be pre-programmed behaviors on how to move. However, these could also trigger a separate decision-making process that could be a function all of its own. So in other words, you could have agents that call other agents to make different decisions. This allows us to make populations of agents that specialize on specific different tasks to complete a larger, more complicated goal. Next, let's look at a slightly more complex agent, a reflex agent that has a state. In this example, the agent is only different because a state is stored of the previous state of the environment. This serves as a form of short-term memory, and it can allow for better selection of rules that are applicable to the situation. This helps us to capture how the world is evolving and what the actions I'm choosing are doing in the context of the environment. Another kind of agent includes goal-based agents. Here, the agent has an explicit goal, and when choosing an action, it will select an action that tries to achieve that goal. In this case, the decision process can require some planning. In other words, what will we expect to happen if I do action A? This kind of agent is even more flexible than a simple reflex agent and is capable of achieving goals that can often require multiple steps. In this case, the agent is making predictions along the way, trying to guess how the next action will change the environment and how it will help us lead to a given goal. Another class of agents are utility-based agents. The main difference here is that not only are we trying to achieve goals, but we're trying to evaluate how well we're achieving them or how quickly we're achieving them. This allows us to conduct goal-based actions where we try and maximize some measure of performance in achieving that goal. You can also think of this as quantifying how well we're achieving a goal. The final and most sophisticated variation of an agent we'll talk about today are learning agents. These are agents that can go beyond some pre-programmed set of rules that determine actions based on a given state, and instead can learn through their experience interacting with the environment. In this situation, we still need some standard or metric for determining performance, and this metric allows us to gain feedback on how well our actions are helping us get to our goal. Here, our decision-making happens in this performance element. We have input from the environment through our sensors, and we use the performance element to make an action prediction. This action can then be conducted in the environment. However, the course of interacting with the environment in this loop, there are opportunities to learn how well our actions are actually reaching our goal, or if they're reaching our goal. This feedback drives the learning element, which can change the performance element and adapt them such that in the future we can make better and better action decisions. Now that you have the basic idea of what kinds of agents there typically exist, let's look at some other definitions of agents from some other authors. This one comes from Woodridge and Jennings. They define some of the characteristics of agents as including autonomy, where agents operate without direct intervention of humans and have control over their actions and internal state. They also describe agents as having social ability. In other words, agents can interact with other agents and possibly humans via some agent communication language. They also describe agents as having reactivity, where agents perceive their environment and respond in a timely and rational fashion to changes that occur within it. Further, agents have proactiveness. They don't simply act in response to their environment, but they're capable of taking the initiative and generating their own goals and act to achieve them. Woodridge and Jennings also describe what they call a stronger notion of what an agent is. So in this case, an agent has mental properties such as knowledge, belief, intention, or obligation. And in addition, an agent has other properties such as mobility. They can move around from one machine to another across different system architectures and platforms. They have veracity. In other words, agents do not knowingly communicate false information. They have benevolence. In other words, agents always try to do what they're asked. And rationality. Agents will try to achieve their goals and not act in such a way to prevent their goals from being achieved. So why should we use agents? Well, agents provide three fundamental abstractions. These include the autonomy abstraction, the cognitive abstraction, and the society of agents abstraction. We'll talk about these more in a second. Computer scientists use abstraction mechanisms all the time, such as procedural abstractions, abstract data types, and the concept of objects in programming. Regarding the autonomy abstraction, this implies the ability to make decisions and to initiate actions without direct human supervision. This allows us to view agents as entities that have goals to achieve and are capable of initiating actions to achieve their goals. Autonomy often implies the notion of persistence and identity. Autonomy also implies the existence of other autonomous entities, and this allows us to see agents as members of a society of agents. Now let's look at the cognitive abstraction. So in everyday life, we use folk psychology to explain and predict the behavior of complex intelligent systems as if they're people. So for example, Maria intended to prepare her slides, or Jane believed it was raining. The term intentional system was coined by Daniel Dennett to describe entities whose behavior can be predicted by the method of attributing belief, desires, and rational acumen. The acronym BDI, which stands for Belief, Desires, and Intention, is used to describe agent architecture that have those properties. The intentional stance is a convenient way of talking about complex systems, which allows us to predict and explain their behavior without having to understand how their individual mechanisms actually work. So let's look at an example of cognitive abstraction. Consider a light switch. It's perfectly coherent to treat a light switch as a very cooperative agent with the capability of transmitting current at will, who invariably transmits current when it believes that we want it transmitted and not otherwise. Here, flicking the switch is simply a way that we can communicate our desires. This is just a simple way of thinking about cognitive abstraction. In this situation, it does not bias anything to think of a light switch this way, since we essentially understand the mechanism sufficiently and we already know the simple mechanistic description of its behavior. However, we frame this example to illustrate how a cognitive abstraction might be more useful in a much more complex agent setting. Next, let's talk a little bit about the society of agents abstraction. So agents don't have to be entities that are living alone. They can be part of a society of agents. And this means that agents can share knowledge, communicate with each other, cooperate, coordinate, and negotiate. However, members of a society can also lie, take advantage of others, and masquerade themselves as someone else. Therefore, social laws need to be developed to ensure that agents deliver what they promise, do no harm to other agents, and act rationally. Here, cooperation can be thought of as working together as a team to achieve a shared goal. Coordination is managing the interdependencies between activities, and negotiation is reaching agreements on matters of common interest. These abstractions should illustrate just how flexible agent-based computing can be and allow us to solve all sorts of simple and complex problems. Some of the specific advantages of agent-based computing include openness. Here, when components of the system are not known in advance, they change over time, and are highly heterogeneous, an agent-based approach allows us to create systems that are flexible, robust, and can adapt to the environment by using their social skills, ability to negotiate with other agents, and the ability to take advantage of opportunities. Agent-based computing can also handle complexity. With large and complex problems, agents offer a natural way to partition the problem into smaller and simpler components that are easier to develop and maintain and are also specialized. Agent-based computing also provides a natural metaphor. Agents provide an easy way to conceptualize metaphors. For instance, an email filtering program can be presented using the metaphor of a personal digital assistant. Another advantage is non-determinism. Ultimately, when talking about a group of agents, it's impossible to predict in advance how they will interact. Agents can learn and change their behavior, and it's not necessarily known ahead of time what other agents will exist and what they will do, especially when part of the system is the development or discovery of new agents. Another cool advantage is that global behavior can emerge from local behavior. What I mean here is that When we're developing an agent, we usually design individual behaviors for that individual agent. However, the global behavior of all of these individual agents working together usually emerges once you go and run the agents, and it's not something you can plan or design easily ahead of time. Minsky's work on the Society of Mind treats agents as individually very simple, but together giving rise to intelligence when acting together. This can happen in certain very special ways in societies. Our last advantage that we'll talk about includes new social laws. Social laws are needed to be developed to ensure that agents deliver what they promise and don't do harm to other agents and act rationally. Agents are to carry out tasks on behalf of the user in an environment where the user has something significant on the line, such as money, reputation, privacy, security, etc. So much like Isaac Asimov's 3 rules of robotics, we can put in place our own rules to help ensure that we get the behaviors we're looking for in solving the tasks that we need completed. One offshoot of the field of agent-based computing is that of artificial life. Here on the left we have a GIF illustrating the idea of cellular automata, where each cell in this grid can be thought of as an agent with pre-programmed behaviors. Based on simple agent-based behaviors, we can see very complex and hard to predict global behaviors emerging that almost look like developing, reproducing, and dying off artificial organisms. We also have examples of trying to evolve different morphologies or locomotions in artificial agents to help them better navigate through an environment. Artificial life is a really cool and interesting area of artificial intelligence research, and if you're interested, I definitely suggest you go take some time and dig around some of this literature. Also, while not the focus of this course, agent-based computing and the idea of agents is definitely a central theme in a lot of different AI research. This introduction was meant as a brief overview of some of the basic concepts behind agent-based computing. Next, we're going to move on to discussing the topic of search, which will be our focus through the rest of this lecture as well as the next 2 lectures. Before diving into the search methods themselves, let's take some time to understand search problems. Most any computational problem requires search. In general, we know the available actions that could be taken to solve a given problem, or these could be the available predictions that could be made, or we might know the available structures of models that could exist. But we don't necessarily know which ones will get you to an optimal, the best, or even any solution. Therefore, we need to examine the possibilities to find one that gives us either a solution or the best solution. This set of all possibilities is known as the problem space, or otherwise referred to as the state space. We'll start by looking at some initial examples of search. So search could be a possible sequence of inference steps in logic to find some proof of some goal. It could also include the sequence of steps required to solve a puzzle, a game, or a task. Or it could be about optimization, where we're trying to find the best solution of all possibilities. Optimization is relevant to things like machine learning modeling, where we're maybe trying to learn the optimal parameter values of a model, or the model configuration, or just what features to include in the model. It can also be about optimizing the hyperparameters, or the knobs that you use to change how the machine learner performs. And so in this case, we might be searching for the optimal set of knob configurations to give us the best machine learner performance. We can actually think of search problems as models themselves. So now let's pick apart some search problems. Here we have a search problem that consists of a state space. We have the example of Pac-Man, and we can include all the positions that Pac-Man could be in, as well as the location of these white dots representing the food that he's trying to consume. In this case, the state space doesn't have any particular order, it's just all the possible configurations of state that the system can possibly have. Then we have the idea of a successor function. Here we have some current or initial state in which the system currently resides. And then we have states that could occur next based on our available actions. So in this case, Pac-Man could head north with a cost of 1 because it's 1 step movement, or it could head east with again a cost of 1 because it's 1 step of movement. These states would be successors of the original state. Any search problem also has a starting state or initial point from which the search begins. And usually they have some goal, something that defines that we've reached the conclusion of our search. A solution to a search problem includes a sequence of actions, in other words a plan, which transforms the start state into the goal state. Now let's walk through some other specific examples of search problems. Our first is traveling in Romania. Here we have a list of cities, represented as nodes, and edges between them indicating travel routes with distances between them. So our state space includes cities. Our successor function indicates roads to which we can travel from any given city, and a cost, in other words, a distance to get from one to the next. In this example, our start state is Arad. We're actually starting at this location. And our goal test is, are we in Bucharest? So we're trying to navigate from Arad to Bucharest, and we're trying to find a solution, a path from one to the other. And our problem could be to find any path, or to find the most efficient path that has the least cost. Here's another example of a search problem. We have an 8-number puzzle where this is our starting state, and we can shift any number to an empty slot and move around the numbers until we reach this goal point where we have a configuration of numbers that looks like this. In this case, any block near an empty space can move either up, down, left, or right into that empty space. This problem is usually solvable in 22 steps on average. However, there are 1.8 times 10 to the 5 different unique states for this problem, and 1.3 times 10 to the 12 states for the 15-number version of this same puzzle. Because of the potential size of this search space, we can't necessarily represent all states explicitly, or expect to search all possible configuration or series of steps. Here is yet another search problem. In this case, we have a map, and we have a robot trying to navigate from this position in the map to this goal position. And we have a wall somewhere here in the middle of the map. Here are states, are positions in the map, and transitions are movements around this map. Again, in this problem, we can move north, south, east, or west, and our goal is to get from start to finish. Remember that an agent that is tasked with solving this problem won't be able to see the entire world necessarily, and instead might only be able to see its neighboring states. Depending on how much of the world we can see and the possible search space, a problem becomes more or less difficult to solve. Here's yet another example of a search problem. Here we're trying to conduct algebraic simplification, starting with this equation and trying to simplify it to something else. Here our set of states are all possible valid configurations of this mathematical function, and operators are available to transform this function in proper ways. And we have some goal state, maybe some simplified version of the equation we're trying to reach, or maybe there's some costs, or maybe there's some metric to evaluate how simple the mathematical function has gotten without knowing a very specific goal state. Another classic example of a search problem is the thought problem involving the wolf, goat, and the cabbage. Here we have a river and a person with a canoe, where we have a cabbage, a sheep, and a wolf on the same side of the river, and we're trying to get them all to the other side. The boat only holds 2 individuals, but you can't leave the goat with the cabbage, or the goat will eat the cabbage, and you can't leave the wolf with the goat, or the wolf will eat the goat. So what are the series of steps in terms of river crossings that the man has to make in order to get all 3 items to the other side without one eating the other? Here our state space includes all valid configurations in the problem. In other words, at any given moment, who is on one side of the river and who's on the other. Our initial state has all 4 individuals on one side of the river, and our goal state is to get all individuals on the other side of the river. Here our successor function is looking at all possible states that are reachable in a single step. In other words, making one step from our current position. For example, a successor of our initial state, where we have all individuals on one side, is that we leave our cabbage and the wolf on one side of the river, and then our person takes the sheep across the river. Once the sheep is on the other side, and the man has returned to the original side of the river, what are the next step successors in this problem? Well, the man could return back across the river empty-handed. The man could take the cabbage across the river and leave the wolf behind. Or the man could take the wolf and leave the cabbage behind. In this example problem, the cost for every step is uniform, or a value of 1 for all arcs, assuming that each trip across the river costs the same amount of effort. So again, in this search problem, we want to find a solution path from our initial state to our goal state, and optionally, depending on the needs of our problem, minimize the cost of the solution. So at the end of the day, all that might matter is that we eventually solve the problem, or we might be trying to find the most efficient, shortest series of steps to get everyone from one side of the river to the other without anyone getting eaten. Here's another classic search problem involving water pitchers. Here we have 2 pitchers, one that holds 7 liters and one that holds 5. And our goal is to get one pitcher that has exactly 1 liter in it. Our successor function allows us to fill up either jug, either from a tap source or from the other jug, or just to empty one of the jugs onto the ground. Here we show a sequence of steps that are required to solve this problem, where we start with a state of both jugs being empty. Without going through the entire solution, I'll walk you through some of the first steps. Again, first we start with our water jugs empty, where we have 5 liters of space in the first jug and 7 liters of space in the other. We fill the 7-liter jug so that now it includes 7 liters. We now fill up the 5-liter jug by pouring the 7 into the 5, leaving 2 liters in the 7-liter jug. Next, we can empty the 5-liter jug, leaving 0 in the 5 and 2 in the 7, and we can now pour the 2 liters from the 7 into the 5. We can then see how the remaining sequence of steps ultimately yields a situation where we have exactly 1 liter in the 7-liter jug. Again, the search problem here is to find this sequence of steps that ultimately leads us to our goal. And optionally, what is the shortest sequence of steps that we might need to conduct to lead us to our goal? Here's yet another famous search example, the traveling salesman problem. We start with a network of cities and distances between them, like we've seen in an earlier example. And the task here is that starting from city 1, the salesman must travel to all cities once and only once before returning home. The distance between each city is given, here on the edges, and is assumed to be the same in both directions. Furthermore, only the links between cities that are shown are able to be used as travel paths. The objective here is to minimize the total distance to be traveled while also reaching the objective of only visiting each city once. This is the kind of search problem that might also be used to plot out ideal road trips. So now that we've looked at a number of examples of search for you to consider, let's dive back into picking apart the search problem. We'll start by asking the question, what is in a state space? Well, before we answer that, we have the idea of a world state, which includes every last detail of the environment, every piece of information you could possibly ever gather. A search state keeps only the details needed for planning or for abstraction to solve the problem. To illustrate this point, let's look at 2 different problems using the Pac-Man example. One where we're trying to find the best path to a new location, and another where we're trying to eat all of the dots. In the pathing example, our states only include the location of Pac-Man, the actions include the direction, and the successor function only updates the location. And finally, the goal here is to end up in a specific location on the map. In this other problem, eat all dots, our states include not only the location, but whether there's a dot or a piece of food at each location. Again, the actions here include moving up, down, left, or right, and there's no eat function here because it's assumed that visiting a location is the same thing as eating that dot. Here, the successor function not only updates the location, but also the state of whether a dot exists or doesn't exist at that specific location. The goal of this problem is to make it so that all dots are false, or they're all gone from this map. Now let's give a little bit more thought to the size of search spaces. So in this example Pac-Man problem, where our goal is to eat all of the food, let's say that there are possible 120 positions that Pac-Man can be in, and he can move or face in any of these 4 directions. Assuming that dots of food can either be there or not at any position, there are a total possibility of 2 to the 30 different food configurations on this whole Pac-Man map. Further, if we have the ghost from Pac-Man navigating around the maze as well, in this example Ghost 1 could have one of 12 positions, and Ghost 2 could have one of 11 positions. Using this information, we can now estimate the total size of the search space of this problem. In this case, 120 positions times 4 movement directions, times 2 to the 30 food configurations, times 12 Ghost 1 positions, times 11 Ghost 2 positions, gives us a total of 6.8 times 10 to the 13 possible state configurations with which to search to find an optimal solution. For a given problem, if the search space is not prohibitively large, it's possible to apply search that systematically and exhaustively searches all paths through the search space. In other words, this will check every state that's reachable from the initial state to find out if it's a goal state. Such methods are also called brute force or blind search techniques, and we can often use what are known as deterministic methods to try and solve these problems. However, for more complex problems, we may need to use something called heuristics. These are also known as useful rules of thumb, and we use these heuristics to better guess which paths are likely to lead to a solution. We'll end this little introduction to search with a formalization of the search procedure. Here we have Q defined as our finite set of states, we have some non-empty set of start states, and a non-empty set of goal states. Here we define our successor function, where we can show Q transitioning to any other new state. The successor function of S is the set of states that can be reached from S in one step, or in other words, one search step. We can also define a cost function, in this case maybe Q by Q, which might be some positive numbers. We can define a specific cost, S comma S prime, as the cost of taking one step transition from state S to S prime. Here our search problem is to find a sequence of steps S1 to Sk, if S1 is our starting state and Sk is our goal state, and we can define successor functions between states. We want our sum of the states from our initial to goal state to be the smallest among all possible sequences of transitions. Notably here, we could either be searching for the absolute optimal solution or just a good one. If we're exhaustively searching a space and look at all possibilities, we know that we can find an optimal solution. However, if it's not possible to search every possible part of a search space, then we can only ever hope to find what we think is a good solution and a potentially optimal solution. Next, let's move on to visualizing search. This will be particularly useful as we dive into the search algorithms themselves. To begin, there are two primary ways to visualize search paths in a search space. The first is with a state space graph, and the second is with a search tree. In a state space graph, every node is a potential state, and every arc between nodes indicates a transition from one starting state to some new state. And here we might see an optimal path to get from our starting to our goal state highlighted in red. Using this same example, we can also create a search tree. Here, our starting state is at the top, and every unique path through the state space graph is illustrated as a unique branch through this tree. Here we can see where our goal lies with respect to our state space graph. And we can see this optimal path from our state space graph illustrated here in the tree, starting from S, moving to D, then to E, then to R, then to F, and finally G. Notice, however, that there are other paths to get to G, such as going from S directly to E, as illustrated as this line in the graph, and then to R, F, and G. While a bit of a review, let's quickly examine the parts of a state space graph. We already learned about networks and graphs earlier, which are made up of vertices or nodes or edges. And graphs can be either directed or undirected. Directed graphs have directionalities between edges. So in other words, you can go from S1 to S0, but not from S0 to S1. While in undirected graphs, you can go either direction. State space graphs are basically mathematical representations of a search problem. The nodes are abstracted world configurations, and arcs represent successors, or the results of making a decision and going from one state to the next. Further, a goal test is a set of goal nodes. Maybe there's only one, or maybe multiple different kinds of goals could be reached. Notably, in a state space graph, every unique state only occurs once. However, as we saw before, this is not necessarily true for state or search trees. Also, notably, we can rarely build this full graph in memory for a lot of real-world search problems, but it's at least a useful idea to allow us to examine how different search algorithms work, as well as to explore solutions to simpler problems. Using our same state space graph example from before, we break it down formally as we've seen earlier. This is our problem space, including all possible states, our starting state, and our goal state. Further, we can define successor functions that show where we can go from one state to the next. So in this case, D can go to either B or C, and actually in this case also to E. And our successor state from start would be to go to P, E, and D. Notably, for our state A, we can't actually go anywhere else, and so our successor function is null. In this example, the cost function for all state transitions is assumed to be 1. Let's similarly now formally define the parts of a search tree. This should be very similar to the trees we learned about earlier in this course. A tree is viewed as a connected, acyclic graph. Again, by acyclic, we mean that you can't go back up to an earlier part of the tree. Here's the Pac-Man example represented as a search tree, where we have some starting point and we have two successor states that are possible based on whether Pac-Man goes north or east. In a search tree, the starting state is always the root node of the tree. Children of the tree correspond to successors, and nodes contain states which ultimately correspond to plans to get to those states, where the plan includes all the successor nodes that came before it going up the tree. Edges are labeled with actions and costs. So in this case, the action was to move north, and we have a cost of 1. Like search graphs, for most problems we can never actually build the whole tree, but we use them here primarily to illustrate how different search algorithms work, or you could use them to solve simpler search problems. One important concept as we get into search algorithms is the idea of expanding the search tree. The term expanding refers to taking a look at what our possible next successor steps might be in our search of a tree. Expanding of the tree happens one node at a time, and we have the term frontier, which describes the set of nodes in the tree that have not yet been expanded. So here the frontier is represented by this shading of green, and our search algorithm might have already looked at all of these nodes not within the frontier. So the question that differentiates one search algorithm from another is which of these nodes in the frontier do we expand or examine next? Another important characteristic of search trees that will become relevant as we look at different algorithms is the idea of the breadth or depth of a given tree. The breadth captures the width of a tree, while the depth captures how many levels the tree goes down, or its depth. We can quantify the number of leaves of a search tree, these lowest level nodes, as being b to the power of d, where b is breadth and d is depth. We often try and describe the time complexity of a search problem based on the breadth or depth of its problem's search tree. So now you should have the basic understanding of the difference between a state space graph and a search tree. Notably, each node in a search tree represents an entire path in the state space graph. So for example, C corresponds to the path from C back to S. And the leaf node G corresponds to this optimal path we've seen in the state space graph. Let's take a closer look at search paths in trees and graphs. So here we have that same optimal search path from our search graph. Here we can see that same path illustrated as a single branch down a search tree. Over here on the right, we show all possible transitions in this search space that takes us to each unique node in our solution space. So S, D, E, P, B, C, and so on. To get to S, we just stay where we are. To get to D, we start at S and move to D. One way to get to E is to start at S, go through D, and then get to E. However, we can also start at S and go directly to E, which exists twice in this tree. In this example, all the unique transitions that we take through the search tree have a red line going through them in this piecewise breakdown. In thinking about how to build a search tree from a search graph, let's also consider this simple four-state graph. If we tried to make a search tree from this graph, we might find that the tree is actually infinite in size. This is because there ends up being loops in this search graph. In other words, you can go from S to A to B, back to A, back to B, back to A, and so on. Therefore, there are infinite possibilities to explore in this search graph, where some of these paths get you to the goal quite quickly, but other paths take you down an infinite rabbit hole where you'd never actually find the goal, depending on the search algorithm you use to search this tree. This is an important consideration in thinking about what search algorithms we might pick to try and solve different problems. The last section of our lecture is going to focus on introducing search algorithms in general. First, let's cover the different types of search algorithms. The first family of search algorithms can be called uninformed search. These include methods like breadth-first search, depth-first search, bidirectional breadth-first search, and iterative deepening. There's also a family of algorithms called heuristic search. These include specific algorithms like hill climbing, uniform cost search, and a couple kinds of what are known as best-first search algorithms, including greedy best-first search and the A-star algorithm. We'll cover these set of algorithms in our next lecture. Then there's also local search algorithms, which we'll cover 2 lectures from now. Additionally, there are search algorithms that deal with constraint satisfaction, adversary search, and population-based search, which we'll also cover 2 lectures from now. Let's start by gaining a basic understanding of what uniform search refers to. This is also referred to as blind search. Here, only the cost between states might be known, but no other extra information is. In other words, you have no clue whether one non-goal state is better than any other, so your search is effectively blind. You don't know if your current exploration down a search path is likely to be fruitful. So uninformed means we only know the goal test. In other words, how do we test to see if we're currently in the goal state? And we only know the successor function, what states can we go to from wherever we are right now. Different uninformed search strategies differ in choosing what unexpanded nodes we want to expand next. Differently, let's look at heuristic search. This is also known as informed search. These are often used when the search space is too big to search every node in it. And instead, maybe it's possible to construct a scoring function to estimate which paths or nodes are more promising to prioritize in search first. In general, you can't be sure you are near your goal, but we might be able to make a good guess. The optimal heuristic search strategy often relies on the type of problem and its underlying complexity, which we often don't know ahead of time. Heuristic search requires an evaluation function that scores a node in the search tree according to how close to the target or goal state it seems to be. Now let's go back to this idea of expansion of nodes while conducting search. Here we have that example problem of the cabbage, sheep, wolf, and man trying to cross a river. And we show a simple example of state transitions trying to get from the initial state to the goal. In general, during the search process, there will be many generated but unexpanded states at any given time. In other words, starting from this node, do we first expand here or do we first expand here? So one has to choose which node to expand next. These uninformed search strategies are often exhaustive. In other words, they keep searching the entire space until the goal is found. Any generated but not yet expanded states form the fringe, or the frontier. And again, in distinguishing our search strategies, the essential difference is which one of the nodes on the fringe do we expand first. In other words, maybe we prioritize deep or shallow expansion. So if this is our fringe or our set of unexpanded nodes, maybe we want to prioritize shallow or the nodes higher up in the tree, or we want to take a deep dive down one of the branches and go deep first. Another precursor to talking about the specific search algorithms is thinking about how to compare search algorithm performance in problem solving. Some of these terms will be familiar from logic. First, we have completeness. Is the algorithm guaranteed to find a solution when there is one? Then there's optimality. Does the strategy find the optimal solution or just a solution? Then there's time complexity. How long does it take to find a solution or the optimal solution? And lastly, space complexity, where we might ask how much memory is needed to perform the search. These last two performance metrics are really important in terms of the practicality of applying a given search algorithm to a given problem. Another formal definition of completeness in search, we have a search algorithm is complete if whenever at least one solution exists, the algorithm is guaranteed to find a solution within a finite amount of time. We have a search algorithm is optimal if, when it finds a solution, it is the best solution. Formally defining time complexity of search algorithm, it's the expression for the worst case amount of time it'll take to run. Time complexity is usually expressed in terms of the maximum path length, m, which captures the depth, and the maximum branching factor, b, which captures the breadth. And lastly, space complexity is an expression for the worst case amount of memory that the algorithm will use. In other words, how many nodes does it need to keep in memory? This complexity is also expressed in terms of the depth and breadth of the search tree. And again, by number of nodes, I mean the number of states that have to be stored by the search algorithm. Let's talk just a little bit more about time complexity as a measurement of algorithm performance. We usually define complexity of a problem as being the complexity of the best algorithm that solves the problem. With respect to time complexity, there's an important and often made distinction between tractable and intractable problems, where intractable problems can't be solved in any reasonable amount of time. Problems that are tractable usually admit an algorithm that takes polynomial time to solve. In other words, time complexity O n to the c for some constant c. Intractable problems are those for which algorithms need exponential time. So they have a value to the power of n, where n is some property of the problem itself, like the tree depth or the tree breadth. So why is this notion of intractability important? Well, here's a quote from Downey and Fellows. Pretty well everyone outside the area of computer science thinks that if your program is running too slowly, what you need is a faster machine. However, just having a faster machine is not the solution to many, many problems. Let's illustrate as an example the difference between two algorithms that run in either time complexity of n to the 2, which would be polynomial time or a tractable problem, versus algorithms that run in time, say, 2 to the power of n, which would be exponential time and considered intractable. Given these two examples, let's look at the time needed for 10 to the power of 10 steps per second. If we have a problem where n in this case has the value listed here, a polynomial problem would scale up in computing time as such, where we can see that even at an n of 1000, it can be solved in a reasonable amount of time. However, with an exponential problem, we can see that as we scale up, we quickly find that we can't solve this problem in any reasonable amount of time frame. Just for comparison, the number of atoms in the universe is around 10 to the 80. And to solve this problem with an n of 1000, we need 7.9 times 10 to the 282 years. We've seen this in an earlier lecture, but here we briefly revisit big O notation that describes the time complexity of problems. It roughly illustrates how code or algorithms slow down as a dataset grows. Here we see our polynomial example and our exponential example from the last slide. Notice that time complexity is not the same as runtime, and the big O notation doesn't necessarily give the precise runtime, but it represents a simplified equation focusing on the most complex term describing the compute time of a problem. So if the compute time can be estimated with this equation, 2 times n plus n to the 2 plus 2 to the n, the most complex term is 2 to the n, which yields our big O notation of big O 2 to the n. This is because as n grows to be a very large number, we can basically drop these other terms, as this one will dominate in the size of the numbers. If you'd like to learn a little bit more about big O notation, here's a table describing a summary of some of the commonly seen big O terms, such as constant, logarithmic, sublinear, linear, quadratic, exponential, and factorial. We can see that there are some example problems, such as the traveling salesman problem we saw earlier, where the traveling salesman problem is considered to be exponential if it's solved using a dynamic programming approach, and considered to be factorial if it's solved using a brute force approach. In today's lecture, we gave an introduction to intelligent agents, mostly focusing on some background information that you're welcome to go and explore further if this area interests you. Next, we dove into some basic concepts involving search problems, looking at some examples and some of the fundamentals of what search involves. Next, we looked at visualizing search, which will be really useful when we get to understanding our different search algorithms in the next lectures. And then lastly, we took a survey of different search algorithms that we'll be learning about in this course and beyond. Here's today's quote. Agent intelligence is a great example of the practical application of machine learning to get everyday work done faster and smarter without having to depend on scarcely available, highly skilled data scientists. Just a reminder that assignment 3 and the final project proposal will both be due fairly soon. Just a reminder that assignment 3 is due and the final project proposal will be due soon. Also note that assignment 4 is now available to take a look at and start. Please check the syllabus for the exact due dates. As always, thank you for your attention, and I'll see you in the next lecture.